So first of all, I just want to say that I did not create the contents of this workshop all by myself. Actually, this workshop was due to collaborating with two other people, and we actually created a workshop for the USAR conference that happened this summer. It was supposed to be in St. Louis, but you know what happened with all conferences this year. And both of these individuals do a lot of stuff with R Spatial. So if you use Twitter, I highly recommend that you give them a follow. If you want to see the original material for this course, because originally this course was 3 hours long, it is on GitHub. And also, you can, I already gave the link, but if there's any latecomers, you can access the materials for the workshop just by clicking on the link. And I know sometimes that there might be issues with seeing the content. So one tip is to press Alt Option plus F to, well, it's either Alt or Option depending on if you use Windows or Mac, to change your aspect ratio of your slides. So just to give an overview of this workshop, if you're not familiar with GIS before, or just working with spatial data, it's very important to first understand the basis of cartography, how all of this works. Because if you don't have a general understanding of that, it is going to be very difficult for you to do the kind of spatial things you want to do moving forward. And this is a lifelong learning process. So please, if you're really interested in this, please continue to read about these concepts after the workshop. So after I give a basis of cartography, I am going to talk about reading and projecting vector data. And then after that, we'll talk about how to draw maps with R using a particular package called tmap. And then if you are familiar with the tidyverse, which is it's like the family of packages that deals with data analysis and data cleaning and scrubbing, we're going to manipulate some vector data using dplyr. And then I'll also give you a roadmap of what you can look at going forward beyond this workshop. So just some important things about how we're going to run this workshop. There are going to be 3 exercises for everyone to complete. I am not sure how familiar you are with R. I assume there might be a range of learners. So we're going to work on these exercises collaboratively. So I'm going to assign people to breakout rooms, and I'll go from one breakout room to another to help people. Please feel free to collaborate with your group members in the breakout rooms. Like if you don't know something and I'm not in the room, please just, ask someone to see if they know it. I've ran this workshop 2 times before, and I've really noticed that this collaborative environment was really useful for participants. And they did work together to do some problem solving. And you're going to have 15 minutes to complete the exercises. So I'm going to time each exercise, and I'll give everyone a warning beforehand, like a 5-minute warning. And we'll try to, I'll give a 5-minute break between the second exercise. Yeah. Okay, so let's jump into it. So let's talk about cartography. Yeah, the Earth's not flat, even though a lot of people, some people believe so. What is a map? Simply speaking, it's a 2-dimensional representation of our planet. And that representation can be in many forms. It can be in a 3D map, or it can be in a 2D map. And you have to project your data in order to create a map. And I'm not going to get into the nitty gritty of all of this, but there's different projections, and certain projections preserve area, some preserve distance, like the infamous Mercator projection. I think that's probably one of the most notorious because it was originally designed for navigation, but if you actually look at a map using the Mercator projection, it actually makes Africa a lot smaller and North America a lot bigger. So you really need to think about, where are you creating a map? What are you creating a map of? Where is it at? And use the proper projection for that. For example, if you're trying to make a map of the United States and you're trying to make a map of Missouri, you should not be using the same projection for those. And in R, when we talk about projections, we talk about a coordinate reference system. And like I said before, you need to know the projection of your data sets. You can do that either by, you can always email us about it, but you can really just also search on Google about it. I'll just say for Missouri, Missouri State Plain East is the projection that I like to use for this area. So please make sure you're using the proper name, because if you don't use the proper name, you're going to get an error message in R. And if you accidentally use the wrong projection, then there might be some calculation errors. When it might look nice on the map, like it might look fine, but when you're doing finer spatial analysis, you might be off by a little bit. So the coordinates reference systems are also changing as well. So the package that we're going to use today for projections is called SF. So any version before 0.9, the CRS was represented by a list with 2 components. And after that, it's going to be referred to with this WKT and this input. And if you want more information, you can just click on the link, in which Jakub, one of the people who helped me make the original workshop, he has a good article on what to expect with this change. So spatial data is, broken up into, I'm not going to cover all of it, but you have the major components are vector data, and then raster data. And as you can see, a geographic information system is a representation of the real world based on this representation of vector and raster data. If you're interested in learning more about this, reading Ian McHarg's book, Design with Nature, talks about this layering that happens in a geographic information systems environment. So vectors are points, lines, and polygons. So points can be, for example, school locations, or lines can be road locations, and polygons can be actual representations of building locations. And this points, polygon, and line data, it is represented in many aspects, but there is an underlying database that pretty much runs under all these type of data. And now we're going to talk about rasters, just to emphasize, we will not be doing any raster manipulation. We are just going to work with only vector data. But it's important to know what raster data is too. And raster data is data that is made up in a grid. and each value represents something. So for example, you might have zeros representing no data, or ones, if you're dealing with land classification, it could mean water. Two could mean a specific type of land, like prairie land or something like that. And a raster is defined by its geographical extension, so numbers of rows or columns, and then its spatial resolution, which is mesh shot size. And so there's many packages for reading geographic data. Before, SP, Argudo, which these are still used, may I add, but when it comes to nowadays, SF and STARS and Terra are more used for raster and vector data. But I still do use Argudo and SP. Okay, so I have a little quiz, and so I don't think I really covered this, but just think about what I mentioned, what is very important when you deal with spatial data. So what is the first question you ask yourself when you have a problem with your spatial data manipulation? So I'll give a context. You are dealing with Missouri data and you're trying to create a map and you're trying to do some spatial analysis, but there is a problem. It is not computing correctly. What will be the first question to ask yourself? All right, so yes, Fatima. B, what is your projection? Usually the first problem is that you used the wrong projection. So always check to see if you have a projection. And in summary, we talked about projections and vector data and raster data. So on to everything is fine with SF. So let's go back to this scenario of you're working with Missouri, a subject that's in Missouri. You have all this spatial data. How do you read and project it? Well, using the SF package, which is what we're going to use today to read in our data, all formats are handled by GDAL. So that can be many types of formats, but the ones that I personally use the most is the Esri shapefile, which is right now the industry standard, but there is a move towards using a geo package. And the reason why is because the Esri shapefile, you have to have a minimum of 4 files. And with the geo package, there's less files to handle. So for me, sometimes I want to copy and paste something from, like if I'm using ArcMap or something, to another folder. But if I forget one of those 4 to 5 files, then my vector data is going to be corrupted. But with the geo package, from my experience, it's less files. Like in some instances, is only like just 2 or something like that. So if you're a shapefile user, I highly recommend you just dabble in with a geo package, because it's always just good to stay updated with what's going on. And so you can use the STCRS to actually see if you have a coordinate reference system. As Fatima answered in the quiz, you have to check your projection if you should check that first if you have a problem. So you can use ST_CRS to see this. And in this slide, this is showing the coordinate system of some departments, I can't really speak French that well, in France. The reason why France was chosen is because the person who was on our team really heading this project for User 2020 is based in Paris. So you're going to see a lot of examples of France in there. So with this set STCRS, you can see all of the projection information for your geospatial data. And let's just say that you want to project your data into new coordinates. You can use st_transform for that. So just one little thing, like for example, if I'm dealing with a CSV file with points and there is no projection, what I usually do is project it twice. So if it's Missouri-based data and it's just a CSV file of points, I first will do the st_transform to WGS84, which is not really a projection in itself, but it gives a reference spatially. And then after that, and that's a CRS 4326. Then after that, I will put it in the appropriate projection. That's also a problem I've noticed with people who do spatial work in R and are just starting out. They will import CSV file, but not first project it in WGS84. So please do that first when dealing with CSV files. And segueing to that, you can not only read in a CSV, but also TXT and XLS with a various reader functions. So reader is another tidyverse package, and you can do read CSV, v_CSV, v_TSV, and so on and so forth. You can also use read dot CSV, and it'll still work, but we're just keeping this all in the tidyverse things. So so CT to everyone. Does the change from Project Spring format to the WKT impacts users of geographic data outside R? I am not sure about that. So, but maybe Jacob's article might actually address that. But at a first hunch, I believe it's only R specific because it's based on the infrastructure of how the spatial data is processed and imported in R. So I don't have like the authoritative answer, but my hunch is probably just an R thing. But I would highly recommend you read the article to see. So, so going back to say working with CSV data, what you will need to do after creating, importing that data and all of that, you need to turn it into a spatial data set. So usually what I'll do is I'll, like in this example, I'll probably have a CSV file called cafe bars. And actually there's something a little similar in the exercises that you're doing. And so I'll read that into a data frame. And then after that, I will transform the cafe bars data frame data into a spatial object using st_as_sf. And this is really important because I messed this up a lot when I was first starting to use a lot of R spatial things. Please make sure to put the longitude first and then the latitude second. In my mind, I always have it flipped. But if you do not do that, you will get a lot of error messages, speaking from experience. So please make sure to put the longitude first and the latitude second. And then let's just say I'm done with dealing with my Missouri CSV data, turned into a spatial object. I'm ready to turn it into a geo package. You can use write_CSV for for that. And as before with ReadCSV, it handles various formats, including the new GeoPackage format. So now we have another quiz. So what is the right way to deal with the following text file with the coordinates to be used as a spatial points data set? The correct answer is A. That is how you turn your data set into a spatial points data set. For B, that only applies for data that's already spatial data sets. And then for C, that only specifies the CRS. And then D, you can't read a text file with a spatial frame object file that's designed to read spatial data. So just to give a summary, I went over the SF package and some of the functionalities for that. Now let's move on to the activity. Does everyone have the link to the project? I'll put it back in here. And I'll actually show what this interface looks like if this is your first time using RStudio Cloud. So everything that you need is right here. I have exercise solutions. Please don't please don't look at that first. I have the presentation. I have the presentation notes and the R Spatial tutorial exercises. So with this, you would need to, you're probably seeing this temporary projects. You are going to need to make this a project of your own. And it should give you the option to do that up here. So are there any issues with that? It might take some time to do that, but please save this as your own project when prompted to. So I'm going to just click on the tutorial exercises. So this is what this looks like. Please make sure to load these packages first. If there's any issues and it's saying, oh, you need to install things, then please uncomment and install everything and then uncomment it again. I mean, comment it again after you're done installing the packages. And pretty much this, these exercises are kind of a role-playing type of exercise that you're showing your friend pre-COVID times. So we're thinking in an alternate reality now. You're showing your friend around in St. Louis, and you're going to do this by creating maps and doing scavenger hunts and things like that. So the first exercise you're going to do is spatial vectors data, read and project, which is this one. You need to fill out the code, the blanks with the code, and just run them. And then you will stop at drawing maps with R. Okay, so I have solved the problem. I am going to paste my project again. And I'm going to just share my screen so you can see what it should look like. And hopefully everybody will also see this as well. So you should see the exercises right here. So now we're going to talk about drawing maps with using the tmap package and playing with the vector data. So you can actually make maps with ggplot2 if you are familiar with making data visualizations with R, or with the base R functions. And also, if you want to make an interactive map, you can use plotly. But packages dedicated for making maps are the ones that are listed. And we're going to use tmap because it's simple. And it also, even though it is classified in the static section, you can switch it where you're using the leaflet package to create interactive maps. So it's nice in that way. So let's first talk about, do you really need a map? Do you really want to draw a map? So first you have to think about what's your question and what are you trying to communicate? And will this map be able to do that in a short amount of time? If you have a meaningful pattern, then maps might be your way to go, might be the way to go. And as you can see, there's this map that shows the cafes and bars in France by the number of cafes per department, which are those administrative units in France. And then you can also visualize it with a bar chart too. But using a map can show some kind of spatial patterns. Click next. Okay, so now we're going to go over some quick visualization rules. So when you use qualitative data, you can use shapes or colors to show your differences. If you have absolute quantitative data, then you can use sizes. And then if you have relative quantitative data, you can use color values. These are just some basic rules. This is only touching the tip of the iceberg. So I would highly recommend going to the link below to see a lecture that talks more about that, because these kind of rules are way beyond the scope of this workshop. But you should at least have some basic guidelines on how to map your data. So as I said before, you can use the read_sf function to read in your spatial data, or whether it's in a geo package or shapefile. So if you are a Python user, I believe it was CT that mentioned he's a Python user. By all means, whatever you're working on with Python when it comes to shapefiles, you can just put it in R, no problem. So now let's kind of talk about some of the functions of tmap. So first you have to do tm shape. You have to call that function. And then after that, depending on what you're trying to map, you're going to do plus and then a subsequent function. And I'm going to show an example here. So first, we're going to start out with the shape of Europe. So this is probably assuming maybe this shape, it could just be like a spatial data set, spatial frame, or polygon or shapefile. And I know I have polygon, so I'm going to do plus tm polygons. And then I'm going to create another layer, which actually is maybe a polygon of my administrative regions. So I do another function that says tm_shape. And then I fill it by the number of departments. Going back to the visualization rules, this is probably not a good example of how you should create a map, but this is purely for demonstration purposes only, just to show that you can layer your data on a map. So Please don't think this is the way you should do it. This is more just showing you that you can do it. And then you can add borders and do it with a particular thickness. So now I'm going to talk about creating thematics maps with tmap. You can add various map elements using tmap, such as the north arrow, such as the scale bar, such as the title. And you do this using the compass, and you can show where you want your north arrow. You can do this by adding the scale bar function, and then the tm_layout, where you can put your title. So it's pretty much what you want. You're going to call a function for it. Okay, it's time for another quiz. So, what is the correct way to draw that map that you saw before, which had the different administrative regions of France? C. Exactly. Because first you have to specify the shape that you want, and then you say it's polygon, and then tm_layout. D would work for, say, that's kind of combining like a tmap and a ggplot2. So you can't do that with tmap. As in A, the tm_symbols, that is for point data sets, not polygons. And B, you have to call in your data with tm_shape. That's why that answer is incorrect. So you were close, Molly, but
I have a question about that, Doris,
mm-hmm.
and forgive me since I joined a little bit late. I didn't see the background on tmap, but so can't automatically like read in this shapefile and tell that it's a polygon shapefile?
No, you have to, for tmap, when you're drawing the map, you have to specify whether it's a point line and polygon by using the specific function. So let me just go back. So you would have to do, tm symbols for points, or tm lines for lines, or tm polygons for polygons.
Oh, cool. Thank you.
Yeah, no problem. Are there any, let me just finish the summary and then I can see if anyone has questions. So in short, we talked about, do you even need a map? And how would you represent that map? And how you would read in a shapefile, and the basic functionality of drawing with tmap. So now we are going to do the next exercise, which you actually have this time. And that would be drawing maps with R. So in this whole, so in this whole storyline, you're showing your friend in St. Louis, you have your list of restaurants and points of interest, and you map that out. You have that all loaded in your RStudio interface. And now, because you really like maps, you decide it's a good idea to make some maps. So in this exercise, you're going to be introduced to what I was talking about in the presentation. And please do it up into manipulating vector data with dplyr. So that would be a total of 1, 2, 3, 4 exercises. So please make sure to fill in the blank with the appropriate function and information within the function that you would need to do the task and the instructions. Now we're going to talk about manipulating vector data using the dplyr package. So if you are familiar with the tidyverse of packages, dplyr is used, as I mentioned before, for data scrubbing. data analysis, and data visualization. So let's talk about just a quick overview about using the SF package. So with SF, your data is rectangular. So we are reading in our departments and this code, and it's turning it into this spatial object, even though it's already a spatial object, but it is. And then when you read the CSV and you look things up, it actually looks similar because the spatial object data, as I said before, runs under a database, which looks the same as a CSV file. So dplyr, in terms of doing your data scrubbing and analysis, and dplyr is a package that uses there's a lot of, they have like a grammar of data manipulation or something like that, but there's various verbs that you can use, so functions in the dplyr package to do what you want to do. Two of these verbs are shown in the example slide. So for attributes, you're going to use select and mutate. So when you mutate something, if you're taking GIS class, that means you're creating a new variables. So just think about when you use the run an expression, the field calculator to create a new field. That's the equivalent of that. And for filtering and arranging, you're using that for your rows. So if you're using QGIS or ArcGIS, select by attribute is what you're doing for that actually. So in this example code, the Bretnon region was selected, which includes 4 administrative divisions. And so another package in the tidyverse is called stringar. So that just changes it to a title case. So this might have been capital letters before, but now it's turned into the first letter of the words capital. And these 3 fields, code department, name of the department, and the region, they were selected out of this set of data, spatial data, and we filtered this out by the region that it's a part of. So that's how this code works. You can also use group by and summarize to merge entities. So that would be like using a union type of function or dissolve type of function using an ArcGIS interface. And this code, it is dissolving all of the regions that you see on the left, the departments, into regions. And so you can do that by, if you look at the first code, you're calling the departments. And one thing I forgot to mention is this pipe operator. So the pipe operator pretty much passes one activity to another. So pretty much this is saying, okay, get my departments, pipe operator. Next, group this by the region. Next, then summarize, which is like merging this into regions. So that's how that works. And the advantage of the pipe operator is that you're not having to repeat your code because this would be a lot lengthier without the pipe operator. It takes some getting used to, but it's actually quite handy. Now we're going to talk about a classic operation in GIS, which is joining data. You can do anything from left join, inner joining, full join. For the sake of time, I will not go over all of them. but one that I use a lot is the left join. So when I have like spatial data X and spatial data Y, if I do a left join, whatever is in like, whatever there's a common attribute in X and Y is going to join to the X shapefile. If you want more information about that, you can look it up in the dplyr documentation. If you check your presentation notes, there is a link that has the link from the dplyr documentation about the join. So I would highly recommend you check it out, because even for me, sometimes I get it all mixed up in my head. And a classic spatial join is to join a CSV file to spatial data. So you'll have your shape file here, and then you'll have maybe another shape file with some demographic information. So, and to do a join, you need a common field called a key. And that's how you're able to do the join. So also the key could be a different name, but have the same information. So I would highly recommend you take a good look at your data. If there's if there's data with the same name, then okay, you got it. But if not, then you're going to have to look deeper and see which key columns are the same. So this is joining the database with the shapefile. So this is an inner join in which all rows from X, it returns all rows from X where there's matching values in Y. And then, so whatever's common in Y, it'll show up and say the shapefile, along with all of the columns from both sets of data. So this is joining the spatial data, the CSV file to the spatial data by a key. So the code underscore department is the same thing as ID underscore department. So always make sure you look at your keys and the information. Look for a key with a common name, and then if not, look at what's underlying the data in each column. Go next. Okay, we have another quiz. So what code do you choose to join the external data set restaurants with the spatial data set France underscore L93 if you want to keep spatial entities where there is a match? Yes, it's D, it's inner join, because you only want to keep what's a match. And that's what inner join does. It'll keep all of the columns for both, but it will only keep what matches with that first one it's being joined to, the other data sets being joined to. Oh, okay, so we are at our last exercise. So just to go back, we're gonna wrap up talking about second steps you can take in spatial handling in R. There is more. There is so much more. And we only talked about the tip of the iceberg here. There are so many functions. You can find a spatial extent. You can even do a spatial left join with your data. And you can run some of the functions that are familiar in a classical GIS software program, such as an intersection, crop union. You can calculate distance between 2 points and find and buffer. But I'm not going to go into that since we don't have time. If you want to learn more about these functions, there is actually a module that we created about those specific functions. So you can refer to the original workshop materials in order to learn how to do that. And at that, I thank you very much.